Today we're going to start global rigidity. So I know in the first lecture or two I did define global rigidity, but I'll remind you of that, and then we're going to start working on generic global rigidity. So basically the aim of the next 3 or 4 lectures is to build up an analogous result to the Pollaczek-Geringer-Leman theorem. So remember, for rigidity, we showed that generically in 2 dimensions, rigidity was equivalent to this graph counting condition. And we showed that then in 3 and higher dimensions, it's not true in general, but we could understand something in some special cases. So we're going to have a similar sort of procedure for global rigidity, but roughly everything gets harder. So let's just get started. So recall that a framework, GP, is globally rigid in d-dimensional space if every other framework that you can realize that graph as, so you realize the same graph G with a different map Q, but it has to be equivalent, which equivalent means the edge lengths are the same in GP as in GQ. So GP is globally rigid if every such GQ is actually just a congruence of P. So the distance between any pair of vertices is the same in both. So not only are the edge lengths the same, but actually the distances between any pair of vertices is also true. So every equivalent framework should be congruent to you, but it's every equivalent framework GQ in the same dimension that GP lives in. Okay. So this is a generalization of, or it's a harder property to be satisfied than rigidity, because in rigidity we cared about locally equivalence implied congruence. So there you had to have a continuous deformation or that moved one framework to the other. Here we can sort of have discrete jumps, so you can pick up part of your framework and move it around. So the sort of very simple example is in 2-dimensional space. This one we know it is rigid, but it's easy to see that if you just reflect through the diagonal, then you can draw a second realization of the same graph. And so this shows it's not globally rigid. If I'd drawn these a bit more carefully, they would have been equivalent, but obviously this distance and this distance are different. So this is a rigid but non-globally rigid framework in 2 dimensions. And so we want to, as I say, we want to understand global rigidity generically, and we want to show it's a property of the graph and what that property of the graph is. It turns out we can do this fully in 1 and 2 dimensions, and so we'll get there. 1 dimension we might get to the end of today's lecture, but 2 dimensions will build up over several lectures. And so the main purpose of today is to prove that there are 2 natural necessary conditions that every globally rigid generic framework, whatever dimension you live in, must satisfy. And so these are a connectivity condition and a redundancy condition. So the first one's relatively straightforward. So let's just jump straight to that. So let me remind you, in case anyone is not so comfortable with the graph theory. So remember, a graph is called K-connected. So K is just some natural number. It's K-connected if G minus S is connected for any subset of vertices with at most K minus 1 elements in it. So you form the graph G minus S by deleting all the vertices in the set S, and every edge that's incident to at least 1 vertex in S gets deleted as well. If no matter how you choose at most K minus 1 vertices, you still remain connected, then the graph was K connected. And there's also a trivial condition. So for example, the complete graph on 4 vertices, for technical reasons, you don't think of it as a 4 connected graph, because, I mean, if you take 4 away, then there's nothing left. So you have to wonder a bit. And what we say is that you need to satisfy, for K connected, you need to satisfy this. So K4, this is a 3 connected graph. It's also a 2 connected, 1 connected. There's nothing saying the K has to be exactly the right number, but this is not 4 connected, and not 5 or 6 or anything higher either. Okay, so why is this connectivity necessary? Well, the K is going to depend on the dimension, but otherwise it's going to be pretty easy to see. So here's the lemma. Take a generically globally rigid framework in d-dimensional space. You don't really need the generic in this result, actually. So you take a globally rigid framework in RD, then the claim is that the graph must be d plus 1 connected. Okay, so as an example, here's a graph that in R2, which is not free connected. So this has a 2-vertex separation given by the 2 that were colored blue that I've just made red. So that 2-vertex separation, if you delete those 2 vertices, you have these 2 left and these 2, and all the edges, all the other edges are incident to one of the 2 red vertices in the top picture, so they disappear. And obviously this has 2 connected components, so it's not connected. And what you see from a geometric perspective is that if you take the line through those 2 vertices, this dotted line through the 2 red vertices, then it's easy to see maybe you fix these 2 and you reflect the other 2 over through that line, and you find a second equivalent but non-congruent realization. So since this graph was not free connected, we can easily see the equivalent but non-congruent realization, which shows the graph is not globally rigid. And in fact, what I've just said there is basically the proof of the lemma in general. So let's just go through it anyway. So if our graph is not d+1 connected, then we have a vertex separating set S of size at most d. And just for simplicity of the argument, assume that S has size d. If it doesn't, just throw in a vertex that's not in the separating set in and do the same thing. Or you can do it even more wild reflections, etc., to it to find the equivalent but non-congruent realizations. So I have this separating set of size at most d, and we're saying it's equal to d. Delete the vertices in the separating set and all their incident edges. We know the graph was not d+1 connected, and this was a separating set S. So we know the graph we get, G minus S, is not connected, so it has some number of connected components. It could be many, but just let H be one of the components and let G1 be everything else. Then you have this picture. So I have my separating set S, I have some component H, and then I have the rest of the graph G, which for some reason I've changed what it's called. So that's G1. And we can do exactly what I said in the 2-dimensional example above. So we can define an equivalent but non-congruent framework by putting P' equal to P for all the vertices, this time on the right-hand side. And you can also put P' equal to P for all the vertices in S. And you can just choose to reflect through the hyperplane determined by the vertices of S. There were D of them. And reflect the vertices in H through that to move them all over the hyperplane and change their distances. So then if you pick any one vertex here and any one vertex here, then their distance will change after the reflection. So that's what I say here. So you set PV' by reflecting PV through the hyperplane determined by the separating set, and you get an equivalent framework GP'. None of the edge lengths have changed, so it's easily to see its equivalent, but some of the distances did change, so it's not congruent, and hence we get a contradiction of the hypothesis that the framework was globally rigid. So as I say, that hopefully it was quite easy, but feel free to just jump in if you have any questions. I am keeping my eye on the chat as well if you want to do it that way.
So I have a question. So we have D vertices in the separator set, right? So do we have any result that says that, up to D vertices you can reflect, and more than after D+1 vertices you cannot reflect?
I'm not sure what you mean. So if I had less than D here, I could just take say there was D-1 here, then just pick one out of here and throw it into the set. It will still be a separating set, so you can just do the same argument.
No, what I mean is if so this separating set has it is less than D+1 connected, right?
Yes.
So I'm asking if it were D+1 connected, you won't be able to reflect.
Correct.
So I'm asking if there is a result that says after D+1 connections you won't be able to reflect, and less than that you will be.
Yes. So I mentioned, maybe I was confusing. So if you assume the generic, which I said you didn't need to for this, but if you wanted to, so if you weren't generic, it's possible that your D-1 things only define a hyperplane. But since if you assume generic, then and you had a D+1 connected graph, then you would need d plus one vertices in a separating set, and they're generic, so they don't define a hyperplane. So
Okay.
you could try and reflect, but you would be, the d plus one points would be spanning all of RD, so
Okay.
you wouldn't be able to do the reflection.
Okay, thank you.
There's comments in the chat. Oh, so Alex is saying, oh, thanks, roughly what I said, but maybe it's worth reading that as well. Okay, so the second necessary condition, and this one we have to get a bit more involved in. The necessary condition is called redundant rigidity, so I first need to define that. So I'm going to talk about it as a property of a graph. You could talk about it as property of a framework if you like, but I'm going to talk about it generically. So a graph is redundantly rigid if, when you delete any edge, it still remains rigid. So you can look at all the possible edges. Every single graph, G minus E, for all E and E, has to be rigid. So every edge has to be redundant. It's not, deleting it doesn't affect the rigidity. So here's a two-dimensional example. This one we said before was rigid. It's clearly not redundantly rigid, because if I delete one of the edges, well, I guess there's two options. Either I could delete an edge like this, and then I have a degree 1 vertex here, which maps around on a circle centered at this neighbor, or instead I could have deleted the diagonal, and then I have a 4 cycle, which you can easily see is not rigid either. So for any edge I delete, this is not rigid. And all I needed to show it was not redundantly rigid was there existed some edge. When I deleted, it's not rigid. This one, on the other hand, is redundantly rigid, because if I delete any edge from K4, I get to the graph I had here, a 4 cycle with a diagonal, and that always is rigid generically. So this is an example of a redundantly rigid graph, but you can have much more complicated examples. And we'll talk a bit more detail about the combinatorics of redundant rigidity in future lectures as well. But for today, we want to just show how it is necessary for global rigidity. Okay, so I have a couple of remarks first. So as long as we're not talking about dimension 1, these two necessary conditions I'm showing you are distinct conditions. So D plus 1 connectivity does not imply redundant rigidity, and redundant rigidity does not imply D plus 1 connectivity. E.g. in the two-dimensional case, here's a simple example of a redundantly rigid graph. If I take any edge away, it's still rigid, but it's clearly not free connected. We already saw this example before. On the other hand, you can be free connected and way too sparse to even be rigid. For example, the Peterson graph, where you can be highly connected without having more highly connected than free, even without having enough edges to be minimally rigid, say in 2 dimensions. So these are very distinct conditions in general. Dimension 1 we'll talk about a bit towards the end. Okay, and the second remark I wanted to make was that since I want to characterize global rigidity as a graph theory property in 2 dimensions, generic global rigidity, it's worth saying that my characterization, which we won't get to today, but when we get to it, will include redundant rigidity. But so I wanted to point out that by the Polacek-Geringer-Lemma theorem, we can express redundant rigidity as a purely combinatorial property in 2-dimensional space. So by that theorem, a graph is redundantly rigid if in 2 dimensions, if after you delete any edge, you still have a spanning 2 free tight subgraph. And so what this means, one consequence of this is that the Pebble game algorithm, which I went through, which checks minimal rigidity in the plane by checking this 2 free tight condition, can also check redundant rigidity in the plane. And in the plane where the D plus 1 is free connected, there are efficient algorithms also for testing free connectivity. So at the global rigidity characterization we're aiming towards, which it will be these 2 properties, the D plus 1 connectivity and redundant rigidity when D equals 2, are nice, and you can test them by fast algorithms. Okay. Okay, so
sorry. The algorithm for testing connectedness, is that just the max flow min cut theorem essentially?
So I think yes, but also no, because I think there are many algorithms for testing K connectivity. So that I don't actually know if the fastest one is a max flow min cut one, but certainly it is one way you can do it.
Okay, great.
And so as the K in K connectivity, as your K gets lower, you get faster and faster algorithms. But so I think maybe it gets more and more clever tricks people can do for low K. So I wouldn't want to try and guess which one they actually use for the current best.
That makes sense. Thanks.
Hey, Tony, could you
Yes.
discuss the first remark one more time? I didn't
Sure.
understand.
What was the first remark? This one.
Yeah.
Yes. So so we've proved that. Let's say we're only talking about dimension 2. So we proved that free connected, every globally rigid graph is free connected. And we're going to prove, the next thing we're going to work on is we're going to prove that every globally rigid graph is redundantly rigid. So that the remark is just saying that these two are distinct properties, that neither one implies the other. So you can satisfy one without satisfying the other. So globally rigid things being one of them does not imply it's the other thing. We have to prove them both separately.
Oh, okay. But in dimension 1, they're apparently the same.
Yeah, so I left dimension one out. We'll come to that at the end. But yes, in dimension 1, it turns out that, well, then they're not quite the same, but one implies the other. But we'll get to that.
Okay, thanks.
Okay, so we want to show this redundant rigidity idea is necessary for global rigidity. And so this is going to be a sort of, I don't know if it's differential geometry or differential topology, so some elementary facts from that we're going to use. We're only going to end up giving a sketch of the proof, but I want to give you as many of the ideas as I can as we go. So remember we defined maybe in the first or second lecture the configuration space for a framework GP. So it's the set of Q in RDV such that GQ is equivalent to GP. So we just have this nice space. And you can make an equivalent formulation of global rigidity if you like quotients. You take this configuration space, quotient by the Euclidean group, and you ask that the equivalence class of the realization you start with is the only realization. So this entire space is just this one equivalence class, and so you can't actually move anywhere else within your space. So you quotiented out by the Euclidean group, so we've got rid of translations, rotations, and reflections. So it's saying that that one equivalence class you've got left is unique, because that's the entire space. Okay, and so in some sense, this is the kind of the rough thing we're going to work with, except I don't like quotienting, so I'm going to do the quotienting part in a more elementary way when we get to the relevant point. Okay, so really everything is going to revolve around one lemma from differential topology. And so just need a couple of definitions. So suppose I have smooth manifolds X and Y, and F is a smooth map between them. Then, I mean, I guess most of you know this, but we say that an element X of the manifold X is a regular point of the map F if the Jacobian derivative of F evaluated X has maximum rank. Otherwise, you might say it's a critical point, but I don't think I'm going to use the word critical further on. And fx is a regular value of f if for all y in the inverse image, y is a regular point of f. So regular points we're used to in rigidity, but we're going to have to work with regular values in what we do today. Although, again, I'm going to skip over some of the difficulty, but these regular values are important, where all y in f inverse fx is a regular point. Okay, so here's the important lemma. I mean, I don't think the proof of this lemma is hard, but it is the sort of where the machinery we're going to use. So we have X and Y as smooth manifolds, a nice smooth map F between these manifolds. And suppose X has dimension M, take a point X in X, and suppose that Fx is a regular value of F. And suppose that the rank of the Jacobian of F evaluated X as T. So I give you all that information. Then the lemma tells you that F inverse Fx is an M, this dimension of the domain of the map, minus t, the rank of the Jacobian dimensional smooth manifold. So we get an m minus t dimensional smooth manifold. Okay. So what's going to happen in our case? Well, F is going to be the rigidity map, which takes, this to remind you, so F takes RdV into RE, and it gives us the list of the edge lengths. So, and so the Jacobian derivative will be the rigidity matrix up to scaling. And so let's say, for example, we're in 2 dimensions. So maybe I should have done that here. So this is from R2V. So the dimension of X is 2V. And suppose you're minimally rigid, then we know the rank of the Jacobian rigidity matrix. And if you can show the regular value things, etc., so the hypotheses are all nicely hold, then our F inverse Fp, which is just the configuration space, will be an m minus t, so 2V minus the rank for minimally rigid, so 2V minus 3, so the 3-dimensional smooth manifold. And the 3 dimensions will just be the translations and rotations. So really it's applying this lemma in this kind of way is what we're going to be doing. Okay. Except I don't really want this number to be 3. And this is why I said this quotient before. And really I want to get rid of the isometries, but instead of quotienting, I want to do it in a slightly more elementary way. So I'm going to apply the lemma to, as I say here, frameworks without isometries. And so that the 3 from the isometries will disappear, and I'll actually get a 0-dimensional manifold for in the case when it's rigid. Okay. So how do I want to avoid isometries without doing the quotienting thing? I want to use standard positions. So I say that a framework GP and RD is in standard position if, and so you can see for yourself how to generalize this to RD, but let me just do it for a couple of dimensions. So when D equals 2, I've got 3 isometries. I've got 2 translations and 1 rotation. So I'm going to pin the 2 translations, rule them out by saying one vertex lies at 0, 0. So by fixing these 2 points, say, let's pretend I always have connected graphs, so I don't have to worry too much. Then pinning 1 vertex will stop the 2 translations. And so then I only need to rule out the rotation. I can do that by putting a second vertex on the axis by just pinning 1 of its coordinates. Okay. In R3, you have 6 isometries. So pinning 1 vertex takes away the 3 translations. And then to take away the 3 rotations, I have to be slightly careful. I couldn't just pin PV2 in at a certain location because that would not rule out all 3 rotations. So what I do is I make the first 2 coordinates of PV2 0 and the final coordinate of PV3 0. And in R4, where you have 10 isometries, 4 translations and 6 rotations, pinning 1 vertex gets rid of the translations, and then you have to split your 6 rotations among 3 different vertices. So I do that like this, and you can sort of imagine now how to extend this to the D+1 choose 2 isometries in D dimensions. You pin 1 vertex, and then you have to worry a little bit about how you do the rotations. And actually there's lots of choice in what you do, but what you can't do is things like what I said before. So in R3, you can't just say, well, I've pinned this vertex and pinned this vertex. That would be, oh, you think PV2 and PV3 might be incorrect. Which line, Alex?
Imagine PV2 is 0, 0, Z. So you've put it on the Z axis.
Mm-hmm.
Then if you're going to rotate around the Z axis to take vertex 3 somewhere, it has to be in the Z and some other component. Like you can't guarantee that the 3rd component is 0. You could guarantee that one of the first 2 is 0. So I think there's a compatibility issue. So if you leave P of V2 like it is, then you need to 0 out either the X component or the Y component of P of V3.
I have to try and imagine a picture in my head. But...
yeah.
So this one.
Yeah, that makes sense.
You agree with Alex, Will?
Yeah. When you rotate around the Z-axis,
Yeah,
you're only able to like say fix the x coordinate to be 0 of P3.
Yeah, I agree as well.
Yeah, okay. Okay, thanks. So yeah, so what you said, Alex, was to do this one instead.
Yeah, I mean, typically I have the zeros creep in from the right, one at a time.
That would have been more sensible if I'd thought through this carefully enough. So yeah, so then in R4 you want it to look like this, if that makes sense.
That would work. That would work.
W2, a Z3, W3, and a Y4, Z4, W4. So the R4 one will also be wrong, but something like this. If you can read right. That scribble, will be okay.
Yep.
Yeah.
I was just doing this the other day, so that's why I spotted it. So.
Great, thanks. Yes, so what that means is that, so now we've put it in standard position, and 2 dimensions it was fine, and then 3 dimension and upwards Alex is fixed. So the GP in standard position is now, I'm going to think of it as a point here. I'm not going to think of it as a point in RDV with loads of zeros. I'm going to think of it as a point in this smaller space. So this is going to change the dimension of the domain when I apply the lemma. So it's going to have this smaller bit, which is going to get rid of the 3 that I had in dimension 2, or the D+1 choose 2 in general. And so to do this, I'm going to define FG to be the restriction of the rigidity map to apply to this domain, so to frameworks in standard position.
Is this what's called pinning?
Yeah, yes, so you can call it, yes. Yeah, effectively what I'm doing is I'm pinning one vertex, and then I'm pinning some of the columns in the rigidity matrix corresponding to the rotations. Okay, so, but notice that I want to talk about generic global rigidity, but I'm introducing non-genericness with these coordinates of these vertices being 0, because if you really want to be algebraically independent, then everything is transcendental, so you certainly can't have zeros. So I want to define a framework to be quasi-generic if it's congruent to a generic framework. So I take a generic framework, and if I translate that generic framework to put a vertex at the origin, and then I rotate to put all the vertices at the 0, 0, etc. points, as we just talked about, then that generic framework will become quasi-generic because I've zeroed out some of the positions, but it still has exactly the same rigidity properties. So the translations and rotations won't affect things. So we'll work with these quasi-generic frameworks, which are ones congruent to a generic framework. So and that's what I say here. So any framework in standard position is non-generic, but if I give you a generic framework, we can always just apply isometries to get a quasi-generic framework in standard position, and they'll have exactly the same global rigidity properties. So there's no loss in generality in thinking about quasi-generic standard position frameworks. Okay. So, yeah, as I said, so the main technical problem about showing redundant rigidity is a necessary condition for global rigidity. We haven't got to the sort of proof technique yet, but the main technical challenge will be in showing we can actually apply the previous lemma. And so what I mean by that is showing the assumption that for this restricted rigidity map F, FGP is a regular value when P is a quasi-generic in standard position. Okay. So, and maybe this is the right point to say that the argument I'm going to present, it's a proof of what's called Hendrickson's conditions, redundant rigidity and D+1 connectivity. But Hendrickson's original proof showed this, but really only showed it in a weaker circumstance. So Hendrickson used Sard's theorem to show that this is true almost all the time. But what we want it to be true is not just almost all the time, but the almost all the time that is every single generic framework. So it was possible from Hendrickson's theorem that the almost all missed some generic and included lots of non-generic, say, but it wasn't quite true for all generic frameworks. So to get that extra bit about all generic frameworks, you need a result from algebraic geometry. So you need sort of some quantifier elimination kind of results. And so Tarski-Seidenberg result, in particular the result, and I'm not even going to go into it, but the proof I'm using is from a paper of mine with Bill Jackson and Tom McCourt, and there the version of Tarski-Seidenberg we used was simply a projection of semi-algebraic sets. Yeah, so I do say it here. So this is what I'm saying, that Hendrickson showed almost all globally rigid frameworks are redundantly rigid. The fact that it's true for all generic globally rigid frameworks really is due to Bob Connolly, and I think that in the literature we just take this extension to be implicit. It's Connolly introduced using these sort of Tarski-Seidenberg things in combination with Sard's theorem in one of his papers, and so the same technique basically it makes Hendrickson's theorem work for all quasi-generic rather than just almost all frameworks. If there's any experts in the room who want to correct me on any of that historical commentary, then please do. Okay, so here's Hendrickson's theorem from '92. So I take a quasi-generic globally rigid framework for D at least 2. So as I said, dimension 1, 2 connectivity and redundant rigidity are linked, so we don't need to worry about that. And there is one place in the proof where it will be useful to be at dimension at least 2, but every such framework is redundantly rigid. Every such globally rigid framework is redundantly rigid. Okay, so let me do sort of a detailed sketch of the proof. So I can apply translations and rotations. So without loss of generality, I can assume my framework lives in standard position. And in standard position means that, for example, the first vertex is fixed and never moves. And so it means that, and say in dimension 2, where the second vertex is at 0, y2, the 0 never changes in for the second vertex either. So we're looking at this restricted rigidity map, and equivalent but non-congruent frameworks have to still have the 0, 0, 0 for the first vertex and for the first half of the second vertex. Okay, so we know global rigidity implies rigidity. So I mean, you can do this argument with just that I'm about to say in a moment if you're dealing with a flexible case, but it's not interesting. So let's just say that globally rigid implies rigid. This is not hard. So now I want to do a contradiction argument. So I suppose that GP is not redundantly rigid, and I want to show find a second equivalent but non-congruent realization which contradicts the assumption that the framework is globally rigid. So I'm assuming it's not redundantly rigid. What does that mean? It means I can choose some edge such that when I delete that edge, it actually becomes flexible. So I have my framework GP, which is rigid. It's a generic rigid framework, but it's not redundantly rigid. So when I throw E away, it becomes flexible. And hence we know the rank exactly, because G was rigid, G minus E is flexible. So we know the rank is exactly 1 less than the Maxwell count. So the rank of the rigidity matrix for G minus E is dV minus D plus 1 choose 2 minus 1. Okay. So now we want to apply the lemma. So as I say, we're taking as given the hard part that this restricted rigidity map for G minus E is a regular value of this restricted rigidity map applied to the graph G minus E. We know the domain of FG minus E is R to the dV minus D plus 1 choose 2. So it's dV minus D plus 1 choose 2 dimensional. And we know the rank. So we know everything we want now to apply the lemma, and that tells us that this inverse image, which we define to be the configuration space for G minus EP, this is a frameworks in standard position. We know this is a dV minus D plus 1 choose 2 minus dV minus D plus 1 choose 2 minus 1 dimensional smooth manifold by the lemma. And so obviously this gives us a nice one-dimensional manifold. Okay, so now it's a one-dimensional manifold. That lemma has really told us a lot about how this when we deleted an edge from a rigid but not redundantly rigid graph, what the configuration space can look like, and we'll use what we know about that to find our second equivalent but non-congruent realization. So in particular, what we're going to do is take our one-dimensional smooth manifold, and next we're going to show it's compact. And actually, if you look at Hendrickson's paper, his proof that it's compact is basically one line. It's very easy. I've added a few more details just in case it's not so easy. For example, from a combinatorial perspective, I thought it was worth adding a few lines to this, but it is quite easy to show it's compact. So we know the configuration space lives in here, so all we have to do is show that it's closed and bounded. So closedness, Hendrickson says it's trivial. Let me just write 3 or 4 lines for it, just to make sure. So take a sequence of points, P1, P2, etc. in our configuration space, which converge to some limit point Q. Then the corresponding frameworks, all these points were in this configuration space, so they're all in standard position, and they're all equivalent to G minus EP. And so they converge to the limit point Q, which is also, so I guess it's easy to see that G minus EQ will also be in standard position and also be equivalent to G minus EP. So our limit point Q is in the same configuration space, so we're closed. So I mean, it's almost tautological, but I just wanted to write out a couple of sentences for it. And then boundedness is the point where we use dimension at least 2, because we know G is rigid, and rigid graphs in dimension at least 2 are at least 2 edge connected. So when we take an edge away from a rigid graph, we're still a connected graph. On the line, this is not true. You can be a tree and be rigid, so you take one edge away and it's no longer connected. But at dimension at least 2, G minus E is always a connected graph, and so the edge lengths are fixed and you're a connected graph, so clearly you can come up with a bound that stops you moving too far away, given you have one vertex pinned at the origin. So boundedness is okay. Note, so I've shown it's one-dimensional compact manifold. I haven't shown the manifold is connected, so we have to worry about which connected component, but this is easy. We just pick the connected component of this configuration space, which contains the P we started with, and then we use the classification of one-dimensional smooth manifold to say that this O, the connected component which contains P, is actually just a circle. It's diffeomorphic to a circle. So topologically, we're just working with a circle. So we have some circle, and we have our point P on it. And so this point P is where the length of I want to think of this point P as where the length of the edge E that we took away in G minus E is the right length it was in GP. So if we get back to the same length as this point P, we'll have found somewhere else with the same length for that edge, and we can add it back, and we'll have an equivalent but non-congruent framework to GP. So now we use the fact that P is generic. So since P is generic, it's not an extreme point for the function which changes the length of this missing edge for E. So there exists a Q1 and a Q2 such that the length of the edge of E in the framework GQ1 and the length of the edge of E in the framework GQ2 are smaller and bigger than the length we want. So I have a Q1 somewhere and a Q2 somewhere else on this circle. And I know one of them is smaller than P and one of them is bigger than P. Okay. And so obviously it's a circle, so there's 2 paths between Q1 and Q2. I could go via P or I could go around the other way. And I can use the intermediate value theorem to find a P1, let's say it's over here, which is not equal to P, because I've been able to go the other way, which has the same length. So Q1 is less than P, length is less than P, Q2, the length is bigger than P. So as I traverse from Q1 the other way around to Q2, I find somewhere else with the same edge length as P, and I call it P1E. So I found GP1, which is equivalent to GP. Okay. So now I want to say I found an equivalent but non-congruent realization, and I'm finished, but I'm not quite, because my pinning only got rid of the continuous isometries. I only got rid of translations and rotations. So it's still possible that P1 is simply a reflection of P, or a composition of reflections of P. But this is also something that's not hard to check, but I'll let you think about that for yourself. So the proof is complete if you can show that P1 is obtained from P by a composition of reflections. Then you do get this non-congruent but equivalent framework GP1, which contradicts global rigidity. Okay. Any questions about, I know there was a couple of points at least where I sketched rather than proved, but any questions before I move on? Okay, so now I want to come back to the one-dimensional case, and I think this was one of the things that was asked about earlier. So in one dimension, d plus one connected means two connected. But if you're a two connected graph, then it's certainly true that if you delete any one edge, your graph remains connected. But every connected graph is rigid in one-dimensional space. So every two connected graph is redundantly rigid on the line. So the two connectivity condition implies the redundant rigidity condition, which so the one dimension one case that I left out from the Hendrickson's theorem is immediate from the two connected necessary condition. And actually more is true. So in one-dimensional space, we have an easy-ish result that if your graph is two connected, you can go the other way as well. So your generic framework on the line is globally rigid if and only if the graph is two connected. I do actually need generic. So if you remember back to the start when we talked about one-dimensional rigidity, we didn't need generic to characterize rigid on the line as graph connectivity. But for global rigidity, even in one dimension, we do need to use generic or quasi-generic, if you like. Okay, so I thought I would give a little example showing that genericness is necessary. So this is the force cycle realized twice on the line. So what's happened here, V1, V2 have been switched in their positions, but you can see the length is the same up to my bad drawing. And V3, V4 have been switched in positions, but again, the lengths are the same. You notice the length here, and that's the V2, V4, which is that one, and this is the V1, V3, which is this one. But you can check that, I mean, if I'd drawn the picture slightly more better, it would probably been easier to see, but you can check that these have the same lengths, but they're not an isometry of each other because V1, V4, that's a long way away, and here V1, V4 is close together. So the non-edges have changed their distance. So these are the same graph, but equivalent but non-congruent realizations. And graph both times, it's two connected. So this would be a counterexample to the theorem if you got rid of the word generic. It's not a counterexample because this particular thing I've drawn here is not generic. Okay. So they both, neither of the realizations are generic. And so I guess what I say here is that the edge lengths are the same in P1 as in P2. I know the edge lengths and not being the same is enough to show you it's not generic, because you just move along. Say from the V2 to V4 to V3, the sum of those two non-generic things tells you how to move from V2 to V3 from its location to location. So the points are not generic either. Okay, so I want to prove this two connectivity is sufficient for global rigidity on the line. There's one thing that we're going to prove next week, at some point next week, which is a result about stress matrices, which I haven't really introduced yet, but we're going to prove it then, but I want to say the proof about this theorem now. So we're going to have some fact that which could take as true for now that we will go into the details of next week. And the fact, well, it's a theorem due to Connolly that there's also, that uses stress matrices, that there's also an alternative proof by Jackson, Jordan, and Zabadka, which uses algebraic number theory instead. It's kind of elementary algebraic number theory, but it's still quite a nice proof. So what does the fact say? It says that the one extension operation preserves global rigidity. And we're going to see it will work in any dimension, but I just want to use the fact that it works in one dimension. Okay, so let's say we have two generic frameworks, GP and HP dash, where if you restrict P dash to G, then you get P, so that the two generic frameworks are related. the graph H is obtained from G by a 1 extension, and the smaller graph G is globally rigid, then the result, the fact, is that the bigger graph is also globally rigid. This is a statement about the line. So our 1 extension takes an edge and subdivides it. So it introduces a new degree 2 vertex and deletes this edge. But we'll see that this is true in d dimensions, and we'll go into some of the details of the proof next week. Okay, so this is a fact we need. Okay, so we know that on the line, every globally rigid framework is 2 connected. We want to prove the converse. I want to take a 2 connected graph and show it's globally rigid. And we're just going to use this fact we've just had, an induction on the number of edges. And actually the only remaining non-trivial bit, other than just saying that the setup is going to be left as an exercise. Okay. So we want to show a 2 connected graph is globally rigid, and we're going to use induction on the number of edges in our 2 connected graph. So the smallest 2 connected graph is K3. It has 3 edges. It's just a complete graph, which is clearly globally rigid. That's an easy case. So suppose we have at least 4 vertices in our 4 edges, and hence 4 vertices in our 2 connected graph. If you can delete some edge and still be 2 connected, then by the induction hypothesis, G minus E is globally rigid, and hence adding E clearly can't destroy the global rigidity. So that's a good case. So we may assume that G minus E is not 2 connected for every edge of the graph. So in other words, you're a minimally 2 connected graph in the sense that deleting any one edge destroys 2 connectivity. Okay, so then here's the exercise, the only bit I'm sort of omitting. This implies that there must be a vertex of degree 2 in your graph. Okay, and so the exercise is to show this, but it's not a hard exercise. It's in my 3rd year undergraduate graph theory course, for example. So we know our minimally 2 connected graph has a vertex of degree 2. Suppose the vertex is called V and it has neighbors x, y. Since it's not the complete graph on 3 vertices, and G is minimally 2 connected, we know that xy is not an edge, and hence we do the inverse of this 1 extension argument. So we take our this is V, this is xy, and we know that this edge is not there, and so we go back the other way and add it in. We add in E equals xy, and we get a smaller graph, which is 2 connected. So we get this graph G minus V plus xy, which is 2 connected. And by induction, that graph is globally rigid. And so I guess H here should be this G minus V plus xy, sorry, is globally rigid. And hence by the fact this operation, 1 extension preserves global rigidity, we're done. And we've shown that our 2 connected graph G, whatever it was, had to be globally rigid as well. Okay, so I've come to the end of what I want to say.